Okay. Hi, class. So if you notice on the announcements on the main page of the course, we have a new mini unit. It's not a full unit on its own. It belongs with thermochemistry. So when you have a test, you'll have a test on this unit, rates of reaction. It's going to be a very small unit, only a couple of days, and thermochemistry at the same time. So I know you probably are still working on your calorimetry online lab, your Gizmo, and that's great. And you may not have seen even yesterday's lesson on enthalpy of formation. So things are happening very quickly. One thing you should know about is that Friday we have a PA day, so I need to put that on the calendar. Maybe I'll do it later. So Friday there is no lesson, and I will not be available if you need any help. So just make note of that, and I think everything will be good. So we have this new package, this rates of reaction package. And so the thermochemistry part of the unit kind of talks about how much energy is created or used up when we do chemical reactions. This part of the unit is about speed, right? Or the rate of a chemical reaction. So how slow or how fast a chemical reaction goes. So we're going to learn about chemical kinetics. And I think I talked about this before when I talked about kinetic energy. The word kinetic is related to movement. So we're going to talk about, again, the movement of particles in a chemical reaction. In a reaction, right? A chemical reaction. So we can measure these a few ways. We can measure them by the disappearance of the reactant. So we can, let's say, make a graph of how much of the reactants we have over time, or we can measure this by the appearance of products, right? So we can track the reactants, how fast they go away, or we can track how fast the products appear. And we can talk about it quantitatively, right? Quantitatively means we will have a number for how fast or how slow the reaction is going. So we need to measure things in numbers. And there are a lot of different ways that we can do this. It says there are many methodologies. Methodology is just a way to do something. Okay, it has the word method in it, right? What is your method? What is your way of doing things? So methodologies is just a word that makes method seem pretty long. So there are many methodologies for measuring the appearance or disappearance of reactants or products. The state of the involved chemicals is what determines how to measure the rate. So, right, there are different strategies for looking at how much gas is there versus how much liquid is there versus how much solid is there versus if things are dissolved. Okay, so let's look at some of these methods. So it says reactions that produce gases can be measured using a gas collection technique. You can see up at the top this gas collection technique. So here we have a chemical reaction that's going on in this piece of glassware. This is an Erlenmeyer flask. And you can see that there is a straw coming out of it. And it's going into something called a, you're gonna love this word, a eudiometer. Okay, a eudiometer measures the volume of the gas. So the idea is the gas goes through this tube and it bubbles up through the liquid, and we can measure how much gas is between the top of the container and where the liquid starts, right? So as more gas collects at the top of this, the water gets pushed down, and this this container will fill up. So that is for gases. That's how we measure the volume of the gas, and then we have to do a lot of math. If you took grade 11 recently, right, that was the last unit in grade 11 was about gases. And we have to compare the volume to the pressure and the temperature. Reactions that involve ions can be measured with conductivity. Conductivity meters. So the idea is the more conductive it is, the more ions. Right? So there are electric machines that you can use to gauge the conductivity of a solution, and then you can link the conductivity to how many ions are there. And there's also pH meters. pH meters are for when we have reactions with acids and bases, right? So we can tell how much, if one of our reactants is an acid, we can tell how much is left by the pH, right? The measurement of how acidic it is, right? So there are some devices that you can, like electronic devices, that you can put one end into a solution and it'll tell you what the pH is. Reactions that involve color changes. So there are some reactions where a color change takes place, and we can measure actually how much color there is using something called a spectrophotometer, right? So you would take a sample of the solution during the reaction and you would put it in this machine, and it would shoot different colors of light at it, and from that it would determine how much of the solution has a color, a very specific color. So how do we measure rate? Okay, recall that a rate of something is anything in which changes over a period of time, right? So when we talk about the rate, right, you see this delta again. Remember, delta means change in. So delta X means the change in the change, in this case, change in the amount. So the amount is changing, and also it's over delta T, right? Delta T means the change in time. So as the time goes on, the whatever you're measuring changes. And if you have taken math recently, right? You may have learned rate as a change in y over a change in x, right? This is all sort of baby calculus, right? Calculus is really all about rates. So we're going to do the absolute minimum of calculus. We're going to find some really easy way to calculate rates and then what to do with them, right? If you've taken physics recently, you might know velocity as a rate, right? So velocity is our fancy physics word that really means is very close in meaning to speed, right? Velocity is a change in position over time. Right? I think that kind of makes sense. Right? So if your car goes from one position to another position very far away in a small amount of time, you have a high speed or high velocity. So what are we changing? This is not chemistry, or sorry, this is chemistry, not physics. So what are we changing? We're not changing distance. So how can we tell how fast a reaction is going? Well, we can measure. So it says change in amount, right? All of these are measurements of amount. So mass, right? We can tell how much of something is there by weighing it, or if we have a, so this is best for solids and liquids. The volume is best for a gas. Moles works for everything, right? That's why we use it so much in chemistry. And concentration works for solutions. Okay, so you can see we have all of our states covered. So concentration will be used most often in the course. So we're going to talk mostly about reactions that happen in between solutions. Okay, so therefore the average rate of a reaction is the change in concentration over the change in time, right? Could it also be the change in grams over the change in time? Sure. Could it also be the change in volume over the change in time? Sure. But for this course, we're using mainly solutions, so it's going to be the change in concentration over the change in time. So we have rate equals delta C over delta T, right? So the change in concentration is delta C, and the change in time is delta T, right? So we don't want to have to write change in concentration over change in time every time we have to calculate something. So this is the short form, okay? So this is our new formula, right? Concentration is measured in moles per liter, okay? The word per actually works like a division sign. So moles per liter literally means the moles over the liters, right? We can write it as a fraction, like moles over liters. Remember, fractions have two parts. We call the top of the fraction, we call it a numerator. And we call the bottom of a fraction a denominator. So the moles, when we write moles per liter as a fraction, the moles is in the numerator part, the liters is in the denominator part. This seconds in our equation is in the denominator of a fraction, right? So when we talk about units for the rate of a chemical reaction, okay, you'll see the liters part and the seconds part, they're at the bottom together, right? Because they're both denominators. And you see the moles part in the numerator, okay? So a lot of people get confused with that. Why, if liter is in the numerator in the formula, why does the unit end up in the denominator? And that's why. If we measure the disappearance of a reactant, the change in concentration will yield a negative number. So disappearance, right? If something is disappearing, right, it's going from a lot of it to less of this, right? So it's going to have a negative rate of change. Okay, as time goes on, the amount of a reactant will go down. For products, they appear, meaning as the reaction goes along, we get more of them. Okay, so our delta C will be positive. Our change in concentration will be positive. Consider this reaction. So we have this reaction here. This is sodium hydroxide, which is a base, and hydrochloric acid, which is an acid. If you mix them together, we will get sodium hydroxide, but it will stay as the sodium ion and I think I said sodium hydroxide. Sodium chloride is our product, right? And sometimes we write sodium chloride as NaCl, but we're going to keep it as ions here. So the Na plus ion and the Cl minus ion, because they really just stay dissolved in the water. It's not like you're getting crystal sodium chloride, crystal salt. You're just getting sodium ions and chlorine ions. And you also get H2O, right? So the front part of the base becomes a cation, becomes a positive ion. The end of the acid becomes an anion, and the OH from the base and the H from the acid, they come together and they make H2O. So for this reaction, does it matter which substance or species that we measure? How could we measure the rate of this reaction? So it says, because the molar ratio is 1:1 for each reactant and product, the rate of reaction is the same regardless of which substance we measure. So think about it this way. If one molecule of sodium hydroxide reacts, we have one less. So this will go down by 1. And it will react with 1 mole of hydrochloric acid. So this will go down by 1. And we will make 1 sodium and 1 chlorine and 1 water, right? So the rate is the same. These guys will all happen in the same amount of time. As soon as the sodium hydroxide and the hydrochloric acid go away, the other 3 are made. Okay, so they appear and disappear at the same rate. So we consider R to be an absolute value. Right? There's only one rate for this reaction, and it's the same for both reactants and all of the products. Okay? If the coefficients were different, like in this equation here, it would be called a relative value. Right? So this one here has what we call a relative value. Right? So things appear and disappear at different rates. But the rates that they appear and disappear at are not random. They're related to each other. Okay, so it says if ammonia is produced at a rate of 4.0 times 10 to the 3 moles per liter second, right? That's our unit. What is the rate of consumption of each product? So ammonia would be this molecule right here, NH3. Okay, and you can see that for every 2 ammonia that are made, only 1 nitrogen is used, right? So the rate at which nitrogen is used is only 1/2 of the rate that ammonia is produced, right? So we have a 4.0 times 10 to the negative 3, and we can multiply it by a fraction, right? 1/2. And that's related to the coefficients, right? For every 2 ammonia produced, only 1 nitrogen is consumed, right? So we get, 2.0 times 10 to the negative 3 moles per liter second, right? And for every 2 ammonia that appear, 3 hydrogen disappear. So we can find the rate of hydrogen. So we have 3. We have 3 hydrogen are consumed for every 2 ammonia that are produced, right? So this would be 3/2 is like 1.5, right? 1.5 times 4 is 6.0 times 10 to the negative 3 moles per liter second. Okay, so you'll notice that the rate of nitrogen is slower, right? Because there's less of it used per ammonia, right? There's less compared to ammonia. It's less, the rate is less than ammonia because the coefficient is less than ammonia. But the rate of hydrogen consumption is much higher because it has a higher coefficient. Okay, so let's do some practice problems together. It says the reaction of permanganate ion and iron 2 ion in an acidic solution gives the following products. So permanganate, don't know if that's on our polyatomic ion sheet, but that's permanganate. I think it is. And iron 2. Both of these are reactants. It says balance the reaction. Remember that occurs in acidic conditions. Oh, okay. We're going to have a little bit of a problem here because we haven't taken electrochemistry. So we're gonna actually skip this one. You can come back and do it after we've done electrochemistry. We don't know how to balance that stuff yet. Okay. It says under certain conditions, ammonia and oxygen can react as shown by the following equation. So we have NH3 plus O2 makes NO and H2O. So it says if the rate of consumption of ammonia gas is measured to be 2.0 times 10 to the negative 2 moles per liter second, what would the rate be for the consumption of oxygen, water vapor, and nitric oxide? So first thing we need to do with this problem is we need to make sure that our chemical equation is balanced. And it doesn't look like it is, okay? Because we have 3 hydrogens on the reactant side and we only have 2 hydrogens on the product side. So we have to fix that. So if we put a 2 in front of NH3 and a 3 in front of H2O, that means we have 6 hydrogens on both sides. We're going to have to put a 2 in front of nitrogen dioxide to even out the nitrogens. So now we have 6 hydrogens on both sides. We have 2 nitrogens on both sides. Let's hope the oxygens can be balanced easily. They cannot be balanced easily because we have 5 oxygens on the product side and we have O2 on the reactant side. So that's not going to work. If you have an odd number of oxygens on the product side and you have O2 on the reactant side to balance them out, what you have to do is and you have an odd number of oxygens, what you have to do is you have to multiply everything by 2. Right? So this 2 will become a 4. This 2 will become a 4. And this 3 will become a 6. So now we have on the product side 4 plus 6, which gives us 10. So that means this oxygen will be 5. Okay, everything is now balanced. And it says, it gives us a rate, but not a rate for everything because everything has different coefficients, or almost everything has different coefficients. The rate will just be for one of these things. It's a relative rate. It's not an absolute rate. So it gives us the rate for ammonia gas, right? So it gives us this. So we have to find the other ones. And this is pretty easy. We're just going to use the coefficients. So I'm going to zoom in a little bit because I just realized this is the PDF. This isn't the Word file, and I have to write. Okay, so we're going to use the rate of ammonia. So 2.0 times 10 to the negative 2 moles per liter second. And then we just have to multiply it by the ratio of oxygen to ammonia. So there's 5 oxygen for every 4 ammonia. So there's 5 oxygen used up for every 4 ammonia that's used up. So this multiplier is more than 1. So our rate is going to go up. And it's going to be, I believe, so if we divide 20 by 4, we get 5 times 5. So this can be 2.5 times 10 to the negative 2 moles per liter second. You definitely don't have to do this in your head. I'm just a very specific type of lazy person who doesn't like to pick up their calculator. Water vapor. Okay, so this one will go here. Water vapor, we need to go down a bit. Water vapor. So we start off with the rate of ammonia again. And then we have water. Now there's 6 water created for every 4 ammonia that we use. So this will be 3.0 times 10 to the negative 2 moles per liter second. And then this last one, nitric oxide, has the same coefficient as ammonia in this equation. So we actually don't have to do any math at all. If they have the same coefficient, they're going to appear and disappear at the same rate. So this will be 2.0 times 10 to the negative 2 moles per liter second. Now, some of these rates are going to be negative and some of these rates are going to be positive. For ammonia and oxygen, the rate should be negative, right? They are disappearing. For nitric oxide and water vapor, they should be positive. Products should be positive because they're appearing. Reactants should be negative because they're disappearing. Okay? It says nitric oxide and oxygen react to form nitrogen dioxide according to the following reaction. Is it balanced? It is not. That's annoying. So we need to balance this. So add a 2 here and a 2 here, and that will give me balanced, I think, right? 2 nitrogens on the reactant side, 2 nitrogens on the product side, 4 oxygens on the reactant side, 4 oxygens on the product side. We're done. If the rate of production of nitrogen gas, nitrogen dioxide, is 4.0 times 10 to the negative 3 moles per liter second, what is the rate of consumption of oxygen gas? So that would be 4.0 times 10 to the negative 3 times, so there is 1 oxygen used, 1 oxygen molecule used, right? Not 1 oxygen atom, for every 2 NO2 created. So this is, the rate is going to be half, right? So this will be 2.0 times 10 to the negative 3. Moles per liter second. Right, you can see that I do that fairly quickly by having just the 4.0 part and not the 10 to the negative 3 part. 10 to the negative 3 really just gives us where the decimal place is, right? So the 4.0 is the actual number part, and the 10 to the negative 3 kind of tells us where the decimal place is. So it says, if there's 3 moles per liter of oxygen gas present in the reaction container, how long will it take for oxygen to be consumed, right? In other words, how long will it take us to run out of oxygen? So, in other words, if we have 2.0 times 10 to the 3, if it's disappearing at 2.0 times 10 to the 3 moles per liter, and, moles per liter second, okay, so this is a rate. So if we, like a speed, if we multiply speed times time, we get distance back. So if we multiply the rate of disappearance by a time, we will get 3.0 moles per liter, right? So this is the rate of disappearance. So the oxygen will run out when we have 3 moles per liter gone, right? So how do we figure this question out? So we're going to end up that time is going to be equal to 2.0 times 10 to the negative 3 moles per liter second that's going to have to go to the other side. It's going to have to, instead of being multiplied by time, it's going to have to be divided by the amount in order to isolate time. I hope that makes sense. So -2, or it doesn't have to be negative. It's just the rate of disappearance. So it doesn't really have to be negative in this equation. So if we, oh, here, let's keep this question within its own boundaries. So time is equal to concentration over rate, right? So the other way you can understand this is this formula that we're going to use is a rearrangement of the one from before, where rate equals concentration over time. If you rearrange this equation so that delta T is isolated, what you're going to have to do is you're going to have to, it says R equals delta C over delta T. This is being divided, so we're going to have to multiply it on the other side. Delta T R equals delta C, and then we have to isolate the R. So this is multiplication, so it's going to be division on the other side. So delta T is equal to delta C divided by R, right? So maybe that might be a little bit helpful into understanding this. So if we do 3.0 moles per liter divided by 2.0 times 10 to the negative 3 moles per liter second, we're going to get, I don't want to do this in my head, but we're going to get 3.0 divided by, need some brackets here, bracket 2.0 times 10 to the exponent negative 3. So this is 1,500 seconds. Okay, so that, what is that in minutes? Divide by 60. 25 minutes. So it's going to take 25 minutes for that to disappear. So that's why our 1,500 seconds, 1,500 seconds times there is 1 minute is 60 seconds. We get 25 minutes. Okay, so what else do we have here? Baking soda is reacted with sulfuric acid. So it says write a balanced equation for this. So baking soda, sodium bicarbonate, which is NaHCO3 plus sulfuric acid is H2SO4. Okay, and they make water. And oh, this one is actually a little bit tricky. Hold on 1 second. I need some more room here. So I'm going to have to squeeze that a little bit smaller. I hope you don't mind. Okay. So they're going to make water and carbon dioxide. And water. So what do we have left? We have NaOH, H2. Oh, sodium sulfate. Okay, so to balance, I think the only thing that we need to do is double the water. And then I think we are, oh, and double the sodium bicarbonate. And then we're balanced. It says if 3.25 grams of baking soda was consumed in 2.0 times 10 to negative 1 seconds, what would the rate of consumption be in grams per second? So when we have rate and they want grams per second, it tells you what to do, right? Because per means divided by. So we're going to take the grams and we're going to divide by 2.0 times 10 to the negative 1 seconds. And so 3.25 divided by basically 0.2 gives us 16.25 grams per second. Right, the rate is more because 2.0 times 10 to the negative 1 is less than a second. So we're getting rid of 3.25 grams in less than a second. So obviously the rate is more because if we had more time, it would consume more substance. What is the rate of consumption of baking soda in moles per second? So in moles per second, we need to multiply the rate in grams per second. We need to change that grams to moles, right? So it's going to be 16.25 grams per second. And we need to divide by the molar mass of sodium bicarbonate. I might this time, for space reasons, look up the molar mass of sodium bicarbonate. Sodium bicarbonate molar mass. It says it's 84.007. So I'm going to say that's 84. Let me think. So sodium is 22.99. Hydrogen is 1.01. So that makes 24 altogether. Carbon is 12.01. So that's 36.01 plus 48. So I'm going to say this is 84.01. So that's moles per gram, right? So you can kind of see that we have a grams in the numerator and a grams in the denominator, and that means they're going to cancel out. Oh, wait, I said divided by. Is it times? It is times. The only way that these will disappear is if this division sign is actually a multiplication sign. So there you go. And what does that equal? So 16.25 times 84.01 gives me 13 65 moles per second. Let's double check that. This is 0.166 grams per second. Okay, so something's wrong here. What's going on here? We have a problem. Let's figure out what the problem is. So it says 3.25 grams of baking soda was consumed in. Oh, it's because it's okay. I understand now. I had this times 10 to the negative 1, and it's actually times 10 to the 1, right? So that's where I went wrong. So 3.25 grams in 2.0 times 10 to the 1 is 20 seconds divided by 20 gives me, okay, yes, I understand now. 0.1625 grams per second. Okay, so we need to change this to 0.1625. And then we need to multiply that by 84.01. And I get what was the rate of consumption of baking soda in moles per second? That should work. Why does it not work? Point 16. Oh, I understand. 25 times 84.01. So that should give me 13.65. But it does not. It says 1.9 millimoles. I think this is wrong. Because we have moles per second. We did the right thing. Okay. I don't understand. So it's 13.65 moles per second. Let's see if I can make that smaller. Okay, and then it says what was the rate of consumption of sulfuric acid in moles per second? So we would have to multiply that by oh, now I know why. Okay. I'm losing my mind. I understand. I understand what I did. Sometimes teachers can be dumb. Sorry. So we do have to, my initial thoughts were correct. We do have to divide this because it's 84.01 grams per mole, not moles per gram. So this is 84.01 grams per 1 mole, right? So if we divided it, it would be 1 mole per 84.01 grams. So 16.25, or sorry, 0.1625 divided by 84.01. Let me try that again. 0.1625 divided by 84.01 gives us, there we go now. 0.0019 moles per liter, right? And that's why they have 1.9 millimoles per liter. That's still something stupid. So it's 0.0019 moles per liter. Right here, they basically decided to change it to millimoles. Right, millimoles work like millimeters work to a meter. So there are 1,000 millimoles in 1 mole. So basically, they multiplied this by 1,000, so we could get like 1.9 instead of 0.019. So that's where we went wrong. And then it says, what is the rate of consumption of sulfuric acid? So sulfuric acid would be half of that. Right, so if I divide it by 2 on my calculator, we divide by 2, we get 0.00097 millimoles per second, or moles per second. And it says, if the same reaction were performed with 14 grams of baking soda, how long will it take for all of the baking soda to be consumed? So we need to know the time. So delta T equals delta C over R. So that's going to be 14 grams. So we need to use the grams rate, 14.0 grams divided by 0.1625 grams per second. And that's going to equal 14 divided by 0.1625 gives me 86 seconds. Okay, so that was your introduction to chemical kinetics, your introduction to measuring rates of reaction and how relative rates are related to each other via their coefficients in balanced chemical equations. That's it for today, and we'll see you tomorrow.